Welcome. I am Aki Mäkivirta. In this episode, we will look at the reasons for acoustic calibration, what you should consider when you are calibrating your monitors, and how GLM4 actually works under the hood. Let's start the deep dive. This is our list of topics to cover. First, we are going to talk about stereophonic reproduction and virtual sound images. Those are the key to actually creating the space, the sound stage. Then we'll talk about shared agreements about the reproduction systems. These are essential in making sure that you can actually deliver correctly what you have recorded, what you have created. Then we'll talk about monitoring loudspeakers and the room and how they work together, how they interact, and how the room can actually influence and change the sound character. Then we need some gear to do the calibration. Let's look at the gear. That includes the measurement microphone, the mic pre for the measurement microphone. We need some software and analysis tools in order to understand what is actually happening in the space. In GLM4, we have some additional capabilities. We actually have the intelligence to figure out how you have to compensate the loudspeakers in order to get to neutral, clean, very well-resolving audio character. Then we'll talk about different methods of measuring acoustics. We'll start with a bit of history, and then we'll talk about the present day most effective ways of taking measurements. Then finally, we'll look at why we need calibration, what kind of sound color changes happen in the listening room, why they happen. We talk about some other problems, the problems of time of flight differences and level differences at the listening location, how these can impact what you hear and what you're working on. And on the way, we will also talk about how the best practices of aligning, calibrating your room have been implemented in GLM4. Being able to understand what you're doing in the studio, whether it's recording, editing, or mixing, or even mastering your material, depends on understanding what you've been able to create. Metering can help you understanding something about the content. You have different kinds of meters available on the market, metering anything from just sound level to loudness and even coherence and space of audio. But meters cannot tell you very much about the signal. By far, the most important tool that you need is your ears. Only by listening to audio, you can understand completely what you have been able to create. How does it sound? How does it work? By listening, you can make judgments and you can check adjustments. You can know if something needs editing or not. In order to do these things, you must be able to trust what you hear from your monitors. Most of the time, when we are doing audio work, we simply follow this principle of what you hear is what you get. This is what you assume. Most of the decision-making in studio is based on absolutely trusting your ears. You're doing adjustments, you're doing edits almost entirely by trusting on what you hear with your own ears. Let's remember that also anyone else is going to evaluate your result the same way, whether it's your customers or anybody else enjoying what you have been able to create. At the same time as we assume that what I hear is what I get, I'm also assuming that what I hear is also what the customer will hear. And what I hear is what actually is being recorded, what is the content of the recording. It just turns out that there are actually many reasons why these two things may not always hold true. This can have a lot to do with the monitoring system, how the monitoring system has been set up, where it is placed, how does the room interact with your monitoring system. All of this will affect on the sound character, the imaging, and it will change potentially what you hear in your monitoring loudspeakers. In order for you to trust and be able to use your ears completely and with confidence in your work, you have to be able to ensure that what you hear is also what is in the recording. What you hear is what the customer will eventually hear. You want to make sure that your monitoring is set up correctly and it will deliver the quality that you need. To make sure that you can achieve this is fundamentally the reason and the aim for this final episode of creating your sonic reference. GLM4 with Smart Active Monitors and Smart Subwoofers will give you all the tools that help you in getting this confidence, knowing that what you hear is actually what you will ultimately deliver. The listening room and placement of the monitors in the room can have a great effect, a great influence on the sound quality and on the precision of imaging. Let's start by looking at what actually needs to be calibrated or compensated for in our monitoring situations. Let's study some case examples of working environments. Here we have a compact stereo workstation. It looks basically very good to my eyes, but the stereo base appears to be a tad wide, or then the listening position is a bit forward. I would like to check the speaker angles. We will get back to that topic a bit later in this presentation. Many times for audio workstations, the desktop is a significant acoustic reflector for audio. Desktop here appears to be small enough not to offer a large reflecting surface. That's good. Also note in the photo that the wall behind the monitor seems to have a little bit of distance to the monitors. This may mean that the audio will wrap around the speaker, spend a little bit of time traveling to the wall behind, and then get reflected and sum together with the direct sound from the monitor. If we are unlucky with the distance, then this may actually be reducing the bass level. I would like to check for this. It's good to know that GLM4 actually offers you complete frequency response data so that you can easily check and fully understand how the listening situation is working. Finally, note that the sidewall in this situation is away at some distance. This creates delay between the direct sound arriving at the listener and the first reflections from the sidewalls are coming back to the listener. When the distances to the sidewalls are large, sound attenuates while it's traveling back and forth, and this will reduce the early reflection level. Both of these things, the time gap and reduction of the early reflection level, can help in clearing the mid-range and improving monitoring precision. In this next example here, we have a larger home studio. The first thing you notice is that the monitors are placed right on the table, and you have pretty large desktop. And the desktop is actually now sitting very near the monitors. Most likely there will be now a significant reflection of audio off the desktop. These kind of reflections arrive very soon after direct audio, and this can be problematic for sound image precision, and this can cause significant mid-range colorations. The second thing you notice is that the monitors are placed much lower than the listener. This forces the listener to be above the monitor's acoustic axis, and this situation can cause sound coloration, particularly close to the crossover regions. Luckily here we can see that we have Genelec coaxial monitors, and these have excellent off-axis signal quality. So in this sense, this is okay, but I would still like to check here how much the large desktop is affecting audio. Looking at the room, we see that the room does not have a huge amount of absorbing materials or sound control. So the next thing I would like to do is to check if you have any room resonances in this space. At low frequencies, rooms with minimal acoustic control can resonate strongly, and this can be really problematic for low frequency precision. In this case, we have SAM monitors, and these monitors can work with GLM4 AutoCal. GLM4 will be able to show you complete acoustic data. This helps you finding the optimal locations for the monitors, for the listening location, and once we have found those, we can finally add the layer of electronic compensations to bring the listening situation to the best possible precision. However, I would start with possibly lifting up the monitors a little. Then I would like to look at the GLM AutoCal measurements to see how the audio looks at the listening position, and then I would work onwards from there to calibrate the system. And after that, I should do some listening tests to evaluate the result. Both examples so far have been showing stereo systems, 2 monitor systems. They are of course much simpler than if you have a surround system or immersive monitoring layout with a much larger number of monitors. In surround and immersive layouts, things tend to get much more complex. We will see much larger acoustic differences between the different locations for monitors. Let's take a couple of examples of these. Here we see a nice layout. You notice that all monitors can be considered freestanding. They are away from the walls. The ceiling is very high and it's far away from the top layer of monitors. If you look closely, you can see that both the walls and the ceiling have a thin layer of acoustic absorbing material. This will be able to clean out the mid and high frequencies. Clearly, this is a well thought out space. However, you notice that the distances from the monitors to the nearest acoustically hard surface varies. This surface can be, for example, the ceiling or the wall close to the monitor. The floor carpeting can provide a little bit of absorbance, but also the floor will tend to reflect some audio. The floor reflection tends to be pretty similar for all the monitors here because the listening location is symmetrically located in the middle, but the wall and ceiling reflections will differ from one monitor to another. For this kind of situation, GLM4 and GLM AutoCal can really offer a very quick way of, first of all, aligning this kind of system, compensating all the monitors acoustically so that they become more similar. And also GLM4 will show just how similar all your monitors have become after all of this has been done. GLM4 is actually an excellent tool for understanding your monitoring system. Our final example here is again an immersive layout. Here it is slightly more obvious that there must be significant sonic differences between the different monitors. Some of the monitors are right at the hard walls or at the hard ceiling. Some monitors, like the three in the front, are freestanding. We should expect to see significant differences acoustically between the monitors. But of course, also in this case, GLM AutoCal can reduce these differences. GLM AutoCal can also place the monitors at the same acoustic delay and adjust the playback levels to be the same at the listening location. This is the perfect way of enabling accurate and reliable monitoring of immersive virtual sound images. Okay, that was some examples of stereo and immersive layouts. We noticed that it's quite easy to overlook the impact of monitor placement, and room characteristics can have a big influence on sound. Our next question is, how do we find out what actually is happening in the room? We want to be able to measure the sound that reaches our ears as the listener. This will help us in understanding if we have placed the monitor in the correct way and if we can trust what we hear from our monitoring system. So let's start looking at methods of finding out what kind of audio our monitors are creating in the room. The simplest and oldest method of figuring out how your monitors are working in the room is to take measurements one frequency at a time. The hardware we need for this is very simple. We need a signal generator, we set the level, then we run the signal to the monitor, and we place the microphone at the listening position, and then we start adjusting the frequency and we read the meter connected to the microphone and start taking note of the level. Then we work through the full audio range of frequencies, and what we end up is called the frequency response. This tells us the audio level and how much variation in the level we have across the audio range of frequencies. Ideally, with the constant input level, we expect to see a constant sound level at the listening position. If this is not the case, we have coloration, and the monitor may therefore exaggerate or underpresent certain details in audio. Usually, most of the variation that we see in this kind of measurement doesn't actually come out of the monitor. The most likely reason for the variation is actually the room and where we have placed the monitors and the listening location in the room. This one frequency at the time method of finding the frequency response is not very good, and it has several drawbacks. It is slow. When the room has significant reverberation, you would have to wait until the level in the room has settled. After this, the room resonances are fully loaded and we can read what is technically called the steady state value of the pressure at that particular frequency, and then we can carry on to the next frequency. This method also cannot enable us to see how much reverberation we have in the room. It doesn't show variation in time. Because of these limitations, actually no one is using this method to look at the room frequency responses. You would use this kind of method, a method similar to this today, to align levels for multi-loudspeaker systems in the simplest case. In that case, you would not use a single frequency signal, but you would have a slightly wider signal in frequencies, something like, for example, a band-limited noise. And then you would be able to use the sound level meter to align the levels. Okay, so how do we make the measurement faster, and how do we have more detail in the measurement? One way of doing this is to use a signal that contains all frequencies simultaneously. A candidate for such a signal is the impulse. People have been creating impulsive signals in many different ways. For acoustical guys, maybe the typical way of quickly checking how a room responds to an impulsive sound is to clap your hands together and then to listen to what kind of decay you have in the room. There are also more sophisticated clapping devices able to create more repeatable claps. For example, such a device you can see on the right in this slide. This clapper comes actually from the Applied Acoustics Journal published in 2008, so clearly there is an interest to having a repeatable clapping. So what kind of information does a clap or an impulse signal give us? We all actually have experience of this. When I clap my hands together, I hear the response. This is the decay of the clapping signal in the room. This is actually called the impulse response of this particular room. In a large hall, this can take a long time to fade out. You can look this up in the Google if you want, but we also have a mathematical technique called the Fourier transform that is able to analyze the content of an impulse response for us. We can actually extract how much level we have in different frequencies by using this technique. You don't actually have to know how Fourier transform works in order to use it. Actually, the Fourier transform is one of the power tools for acoustical studies these days, and most of the audio analysis software are using it widely. Also, GLM4 software uses the Fourier transform in different ways. So what kind of a clap or impulse would be perfect for acoustic measurements? Let's find out by applying the Fourier transform. Here you can see from left to right pulses that get shorter in time. We start with a 5 millisecond long pulse. It contains plenty of level up to 100 Hz. So this kind of signal would be good enough for subwoofer measurements. When we start making the pulse shorter, we see that the flat top extends to higher and higher frequencies. Finally, when the pulse becomes sufficiently short, we are able to cover the full audio band of frequencies. You also notice that we have a constant level. We have the same level at all frequencies. This kind of pulse would be a perfect candidate for audio measurements. In order to make a signal that has an equal level at all frequencies, we just would have to make the pulse short enough in duration. Now, instead of having a clapper, we can simply feed this signal into, say, a high-quality loudspeaker. Then, when the impulse plays out, we can use a microphone to capture the impulse response of the room. If we now also apply the Fourier transform, we can see what the ingoing signal contains, how much level it contains in frequency, and what happens in the room. So what kind of frequency response are we experiencing in the room? There are some challenges with using pulses as signals for measurement. One of the problems here is the pulse that covers all audio frequencies has to be extremely short. In order to obtain a meaningful and reliable repeatable measurement, we would have to have sufficient energy in the signal in order to generate sufficient level in our measurement. With an impulse, this becomes a problem because the impulse is so short, it cannot carry a significant amount of energy unless it has a huge magnitude. If we start increasing the impulse magnitude, we easily overload the capacity of any loudspeaker to deal with that. So this is a fundamental problem that is present if you want to use directly an impulse as the test signal. Instead of using an impulse, we can also use a sinusoidal sweep that sweeps through all frequencies at the same level. This kind of a signal is much easier to handle than a pulse, and it offers also some interesting benefits when we adjust the sweep speed. Keeping the level constant, if we slow down the speed of sweeping, we can actually increase the energy density in this type of test signal. So we can select at what frequencies we want higher energy level. So by speed adjusting this sinusoidal sweep, we are able to optimize our test signal for best signal-to-noise ratio. This slide explains how we can create an impulse response using the sinusoid sweeps. When we apply the Fourier transform to the sweep signal going into the loudspeaker and the response that we record at the microphone, we can then find out how much level they contain at different frequencies. When we compare the two signals, we can find how the monitor and the room have changed the ingoing signal. Then we can apply the inverse of the Fourier transform. This is a backward transformation where we come from the frequency domain to time domain. This inverse transform is actually able to find us the signal that behaves in a way that creates that level variation that we saw. It turns out that this inverse transform creates us the impulse response. So by using the sinusoidal sweep, we have been able to not clip our monitor. We have been able to get a reliable measurement. We have been able to find how much level we have at different frequencies. In other words, we have been able to extract the room frequency response. We are also able to find out when different parts of the audio arrive at the listening position. We are able to extract reflections of audio, and we are able to see how the room impulse response decays over time. GLM AutoCal uses the sinusoidal sweep as a test signal with carefully adjusted speed variation in order to get the maximum signal-to-noise ratio for all acoustic measurements. This sinusoidal sweep signal starts slow at low frequencies in order to have ample energy density at the low frequencies where it's needed, and then speeds up towards high frequencies, optimizing the signal-to-noise across frequency for room measurements. This test signal is built in all Genelec monitors and subwoofers. And when you have a built-in test signal, this means that you will always have the perfect test signal available for you. GLM AutoCal is an all-in-one solution that offers you everything you need for reliable system calibration in order to make sure that in all situations you will get the most reliable measurement. Let's talk about that next. Having the test signal built into all monitors and subwoofers has several benefits. You don't have to pull the signal cable from any device into the monitor in order to calibrate the monitor. This makes calibration very fast. You cannot make any errors in cabling because you don't have any cables to connect. The GLM network asks the generator in the monitor or subwoofer to start creating the test signal. For this, you need the GLM network connected. Because the GLM network doesn't carry any audio, the network quality and how you connect the network cable is not going to change the measurement result. When the GLM network talks to the monitors and subwoofers and asks the test signals to be output, you always get a perfect test signal. The next thing we have to make sure is that we have an accurate measurement microphone. The GLM kit contains an adapter device and a measurement microphone. Both of these have been built and tested individually at the Genelec factory. Every microphone is individually calibrated. The adapter device contains a dedicated microphone, power supply, microphone amplifier that has been designed to have very flat frequency response in order to be reliable for acoustical measurements. So when GLM4 asks a monitor to output the test signal, then GLM4 is able to start listening to the microphone and collect the room response. When GLM4 asks a monitor to output a test signal, then GLM4 also starts listening to the microphone and collecting the room response. The GLM measurement microphone has been designed to be placed at the listener's ear height and at the listening position. Because the microphone has been designed and calibrated to work when it's pointing upwards, it means that all directions around the microphone on the horizontal plane have exactly the same frequency response to the microphone capsule. For immersive systems, the higher and lower monitor layers have the same frequency response at the microphone in the frequencies where GLM4 is performing the automatic calibration. When studying the frequency response curves, it's good to remember that the very high frequencies will have a slight boost for audio coming from the top layer and directly above the microphone. But this would only be significant when you are looking at the curves. You have to remember this. Once all the measurements in the room have been collected, then GLM goes to talk to Genelec Cloud Computer. The Genelec Cloud Computer calculates the impulse responses, calculates the frequency responses, and then also takes additional steps to figure out how each monitor and subwoofer has to be adjusted to give the best, the cleanest audio at the location where it has been installed. Also, the cloud computer figures out how the levels and delays have to be adjusted in order to align the loudspeakers to have the same level. GLM4 with the GLM kit is the perfect all-in-one system for calibrating your loudspeakers. You can calibrate any size of a monitoring system from mono and stereo to over 80 monitors and subwoofers in one room. And it's fully automatic, so it's a very easy process. GLM4 also gives you full access to all details of the acoustic measurements and to all details of the individual compensations. You can see how similar your monitors are. You can see each and every acoustic effects that your room creates. You can fully understand how your system is performing, how it has been set up. You can use GLM4 actually as a tool to optimize the locations of your monitors and subwoofers, and then you can really fully understand what is happening at the listening position. Next, let's look at the key principles that enable sound reproduction systems to work. And then let's look at what are the typical acoustic challenges or problems that we encounter. Here we have the basic stereo setup. The key concept with this kind of setup is that these two loudspeakers can create virtual sound images, a sound stage between the monitors. A lot of creativity actually goes into placing and engineering these virtual sound images. By using this sound image phenomenon, we create space and depth. All these audio presentation details exist only when we follow the important agreements. For two-channel stereo, we have agreed that monitors are placed at equal distance from each other and equal distance from the listener. And this results in a plus-minus 30-degree angle left and right. This kind of arrangement also implies that the level delivered from each loudspeaker is the same at the listening position, and the delay or the time of flight for audio to the listening position is the same from both monitors. So we have three parts in this agreement: monitor direction, level alignment, and delay alignment. A long time ago, when two-channel reproduction systems were invented, we could have decided to place the stereo pair at any angle relative to the listener. The plus-minus 30 degrees is basically just an arbitrary angle. But today, if the studio setup doesn't follow this agreement, then things become very tricky. For example, if the monitors are placed too wide, this will stretch the audio image and we start getting very unstable imaging in the center. If mixing happens with the monitors having been placed too wide, then the final listening, when it happens in the standard setup, all the images will not spread out in the way that you originally intended in the studio. The audio presentation at the reproduction end appears to be too narrow and crammed in the middle. If mixing happens with the monitors placed too narrow, then the soundstage engineered in the studio can appear to stretch out at home and lose the normal structure in the middle. Ability of the monitor system to deliver imaging is one of the key capabilities. Once we have an agreement about setting up the sound system, it's important that we make sure we follow this agreement in the studio. This ensures that the work translates to home, the consumer. Working with skewed monitor layouts will lead to wrong understanding of the content of the mix. Today, we have much more complex sound reproduction systems. These new reproduction systems surround or immerse the listener, and they can present complete sound spaces. We need a lot of loudspeakers for these. But the same principles also apply for surround and immersive layouts. It's important to follow what has been agreed for directions of monitors and aligning the system for level and delay at the listening location. One of the key tools in building soundstage structure is panning. For 2-channel stereo, the panning can place the sound image between the 2 monitors. For multi-channel and immersive systems, we also use panning, but it's slightly more sophisticated. Typically, this kind of panning uses more than 2 monitors to place audio. On the right on this slide, we can see the VPAB, vector-based panning. This will use 3 monitors, and you can place the audio not only horizontally, but also vertically into a certain location. Let's look at the case where 2 monitors have different delay for audio to reach the listening position. We don't know the reason for this, but it is not very untypical to have this kind of problem in a stereo system or in a multi-channel system. The delay difference will move audio images, and this will have an influence to the mixing work. Actually, less than 1 millisecond of delay difference will entirely pan audio into the nearest monitor. If you think of the distance difference, it's not a huge distance. 1 millisecond is about 340 millimeters or 13.5 inches. Listening to audio in studio and building the soundstage, placing the virtual sound images, we would use panning to align the sound images. But if we have this kind of distance difference, then our panning would not be correct. Looking at the graph on the right, we can see that we can't actually exchange level for delay. It doesn't work because we seem to have a non-linear relationship between the two. The outcome of using level panning with non-aligned monitor system will not be what you expect. Particularly once your recording leaves your studio, it will never sound as you intended. In order to do reliable work, we have to make sure that we follow the agreed layout, we have the monitor directions correct, and we have to ensure that the levels and delays are properly aligned. GLM4 helps you fixing the distance and level differences because it takes measurements. It will find out what the level and distance differences actually are, and it can even apply compensations for these things. But you still have to put the monitors in the correct direction in order to have a completely working system. So everything's looking good, but we still have to face the challenge of room acoustics, and how the monitors interact with the room can still cause us a lot of challenges. Let's take a look at how room acoustics will affect us and how monitor placement will influence the audio. And let's see how GLM4 can improve the quality of monitoring with these things. When we are monitoring, audio is affected by, of course, audio source quality, monitoring loudspeaker quality, room acoustics, and then finally, your ability to hear details will be the ultimate limit. The quality of the monitor loudspeaker is, of course, the key to reliable monitoring. This is the area where Genelec has been working now for 4 decades and is continually improving the quality of audio that we deliver. Despite this, the listening room will have a big influence on audio quality. Smart monitors and GLM4 offer essential tools to deal with monitor influence and deal with the challenges of room acoustics. The first of the room acoustic challenges are the reflections from walls, ceiling, floor, your work surface or desktop, and the other equipment and furniture that you have in the room. All these can reflect audio, and the reflections deliver a bit of audio to your ears with some delay, and this will have an effect on what you hear. This is an example of just having 3 early reflections. Without the reflections, we have a perfectly flat and ideal frequency response at the listening location. With the reflections, the frequency response changes, audio becomes colored. Timing and level of the early reflections relative to the direct audio will determine how the sound color changes. Timing and level of the early reflections relative to the direct audio will determine how the frequency response, how the sound color changes. In this example here, we have a model with direct sound and only one reflection. The early reflection that we have here can move in level and time. The early reflection causes level variation. This is called COM filtering. If the early reflection arrives immediately after the direct sound, we can see this up-down variation, and the variation is sparse, and having this kind of sparse variation or COM filtering is very audible. If the early reflection arrives right after the direct sound, this up-down variation in level is sparse in frequency, and this makes the COM filtering audible. If the early reflection level reduces, the up-down variation also reduces. When the early reflection is down by 20 dB or more relative to the direct sound, most of the time the COM filtering becomes inaudible. When the early reflection moves to happen later, making the time gap between the direct sound and the arrival of the early reflection larger, the COM filter becomes more dense, and this actually reduces the audibility of the COM filter. The standardization body ITU has recommended that early reflections during the first 15 milliseconds after direct sound should be more than 10 dB below the direct sound. The 10 dB limit implies that the COM filter level variation is 6 dB. That's a lot. If possible, we should have better systems than that. GLM AutoCal can show you all of these effects in the frequency response, and GLM AutoCal can also offer you compensations for this. For example, when you have a significant reflection of a large desktop or working surface, GLM can find out the sound influence and can compensate for that. When you place a monitor close to a wall, there will be buildup of level at low frequencies, and this will change the low frequency emphasis. Again, GLM4 can give you full understanding of this influence at the listening location and can offer you precise compensation for this sound coloration and remove it. Rooms resonate. Particularly at low frequencies, the resonances can create areas where you have either too little level or too much level. If you happen to be located, if you're listening at the position of the peak level, then certain frequencies will be way too high. If you are listening close to a notch, you may have the feeling that there is a hole in your bass response and a section of your bass frequencies is missing. Resonances store energy. At resonance frequencies, the sound level increases and the sound decay reduces. Room resonances can cause unwanted and misleading masking of audio at higher frequencies. This can hide details in your mix that you would want to hear and work with. Room resonances can also lead to wrong EQ adjustments. If you EQ your track to actually compensate for a resonance in the listening room, this will sound very weird when somebody plays your recording in another room that doesn't have this resonance. GLM4 AutoCal can measure these problems, can show you how large they are, and in certain cases it can offer you excellent compensations to reduce and remove these effects. This can be quite effective, for example, with subwoofers. However, if your room shows significant resonances, as the first step you should try and see if there's anything you can do to fix the room, and at least you should go and select good locations for your monitors and subwoofers in the room so that they are able to radiate audio without missing any critical bands of frequencies. GLM4 offers you access to full acoustic detail. You can see all measurements for all monitors and subwoofers. You will also see all the automatically assigned compensations. You have the full freedom to evaluate any and all of the settings put in by GLM to see if they make sense, if they improve the audio quality in your room, in your listening position. GLM4 is the most sophisticated and the most complete monitoring setup calibration tool. It's fully automatic and yet allows you to access all data and see all details. It gives you full control and it helps you work with full confidence to what you hear. With GLM4, what you hear is what you have, and also what everybody else will hear in your recordings. This completes our deep dive into the technology behind GLM4. Let's make a quick summary. The 6 steps to create your sonic reference are: the first step, of course, the quality of monitors is the key to hearing all the details in audio. We take care of that side of things. But you select the room. When you do, select a room that does not have very strong modal resonances. Select a room where the reverberation time is relatively small. Consider doing some room treatment. Secondly, place your monitors with care. Avoid reflecting surfaces close to the monitors. Keep the arrangement left-right symmetrical. Thirdly, use GLM4 to calibrate your system. Then study the resulting calibration. If you see big issues, consider rearranging the monitor positions and the listening location. Then repeat the calibration to learn more. This helps you find the optimum solution in your room. When the curves look promising, spend time in listening to your monitoring system. Use material you know. If everything is not 100% in place, then again consider the monitor placement and consider the location of the listening position again. And number 5, spend time to learn the sound in your room. To get to a familiar sound balance for you personally, consider using the sound character profile. You can also save your personal settings in your setup file so they are always accessible to you. And then finally, find the listening level that gives you access to all the detail when you're doing the work. Store that level so that you can quickly get back to that level. So standardize the listening level for you. Then keep checking your work every now and then using your standard level. Your level is going to affect how you hear details, particularly at low and high frequencies, and how you understand the sound color balance. It will also affect how you hear reverberant tails and other details in audio. Now we've completed creating a situation that can offer you a solid background for your editing and recording decisions. Now you have a sonic reference that you can trust. Thank you for joining our series. I am Aki Mäkivirta. We'd be very happy to hear your feedback so that we can take it into account when we are planning our next series. So please email to us at glearninglab@genelec.com.